Hello friends, welcome to Explore Physics. We are starting this video from problem number 56 of GRE paper 0177. This problem states that a balloon is to be filled with helium and used to suspend a mass of 300 kg in air. We have a balloon. This is filled with helium gas and a block of 300 kg is to be suspended from an air due to the upthrust force on this balloon. If the mass of the balloon is neglected, if we neglect the mass of the balloon itself, which of the following gives approximate volume of helium? So how much volume of helium we have required to suspend this mass of 300 kg in air if we neglect the mass of this balloon? So there are three things in this problem. One is the mass of 300 kg have to suspend, and a second is helium. So there are two type of forces acting on helium. One is its mass downward, and the second is its upthrust force and air due to buoyant force. A buoyant force, this will act on the helium upward. A mass of the helium itself will act downward. Weight and weight of the block, this is 300 kg. So we have to find the required volume to suspend this mass. Now, according to Archimedes principle, an upthrust force will always equal to, according to Archimedes principle, an upthrust force will be equal to the weight of fluid displaced. This is a balloon filled with helium gas. An upthrust force is acting upward and its weight is acting downward. This balloon will displace some mass of some weight of air from this region. So the weight of the air will be equal to the upthrust force on this balloon according to Archimedes principle. So there will be three forces. There will be three forces total. The first force is the upthrust force on balloon. Second is the weight of the helium, and third is the weight of this mass m. Weight of this mass. So the net force will be 0, so that so we can suspend this mass. Now this is the upthrust force. This will be equal to the weight of air. The weight of air displaced according to Archimedes principle. So this is the weight of helium. So this is the weight of this mass equal to 0. We can write all these m of air into g minus m of helium and g minus m g, this equal to 0. So the mass equal to volume multiplied by density. We have given a density of air and density of helium, so the volume will be equal. Volume of air and volume of helium will be equal, because equal helium will displace equal volume of air from this region. So we denote a volume by V for both, and this is a density rho of air G minus this is a volume and a rho of helium. For helium, density of helium G minus m G, this equal to 0. If we cancel G from these three terms, we get volume into density of air minus volume into density of helium minus mass of this block. So net equal to 0. We can extract volume V into density of air minus density of helium equal to m. Display, so shifting m to the other side, V, this is equal to m divided by rho air minus rho helium. So this is equal to 300 divided by 1.29 minus 0.1 3.18. If we solve this, if we solve these two, so we will get answer which will be equal to 1.29 minus 0.18 and 300 divided by answer. So this will be equal to 270 meter cube. So D is our right option. We have required 270 meter cube of helium to suspend a mass of 300 kg in air. Next problem. A stream of water of density rho, cross-sectional area A and speed v strikes a wall that is perpendicular to the direction of stream as shown in figure. This is a wall and this is a stream of water flowing in this direction. It strikes the wall here. After that it strikes the wall, the water then flows sideways. The force exerted by the stream on wall is, we have a stream of water that is flowing perpendicular to a wall. It strikes a wall and after striking it moves sideways. So we have to find a force that will this stream exert on the wall. So we have to find a formula for force exerted on it. So we have two methods. The first is a dimensional analysis. We will find the dimension of each formulas. We will mention which of the following is same to that of the force. So that is a density. For density, this is kg per meter cube. Kg per meter cube multiplied by, this is velocity, meter per second square, this is area, so this should equal to meter square. If we calculate, this is a meter square, meter 4, this will cancel with this will equal to kg meter and this will per second square. This is a dimension for the first one. Similarly, if we can find, that is the kg per meter cube, multiplied by meter per second multiplied by meter square. So this is a 2 is a constant, so we can see that this is equal to kg per second. This is not equal to force. This one is equal to force. This is the same dimension as Newton, which is equal to force. Similarly, this is also, we can see that kg per meter cube multiplied by g, this is a meter per second square, multiplied by h is a meter and this is a meter square. So this will become kg multiplied by m power 4 divided by m square, m cube multiplied and second square. This will become kg meter per second square. This is also equal to 4 kg meter per second square, that is also equal to Newton, and the dimension of these both are not same to that of the force. Now, because this term include the velocity term and this is independent of velocity, so we take the first part, that this is the pressure exerted by the water due to its velocity. Secondly, we can verify this by a formula, that is the for momentum. We can know that force, this is equal to time rate of change of momentum, and also we know that momentum, this is equal to mass multiplied by velocity. Now mass is equal to rho v, this is volume, and this is v for speed, this is equal to momentum. We can write here that change in momentum, this is equal to rho multiplied by velocity multiplied by v, which is equal to velocity of the water divided by delta t. Because we can see that the water after striking, there is no horizontal motion, so there is no change in momentum in the horizontal direction. So we can see that this is equal to rho into v divided by t multiplied by v. This is rho divided by T. This is equal to time rate of change of volume. This is equal to flow rate, which is equal to area multiplied by velocity from equation of continuity. So we can put here that density multiplied by area multiplied by velocity multiplied by this velocity. So this will be equal to rho v square A. This is the force that this water will exert on the wall if it strike. So part A is our right option. In this problem we have used two methods. One is the definition, Newton's second law, standard definition of force. This is rate of change of momentum. So we find the force exerted by the water on the wall. And the second is dimension analysis. In dimension analysis we get two option which is correct. This is a force also, and this is also a force. These three terms are not equal to force, are not forces. So these two are force, because here the pressure is, here the force on the wall is due to the velocity of the water. So therefore we take this term, because this includes will include velocity of the water, and this is this term is related to the height, which is means the potential energy of the fluid, and this is due to the kinetic energy of the fluid. And we can see that this is due to the momentum, due to the kinetic energy. This pressure is due to the kinetic energy of the water. So therefore we are taking this term. So both the methods are correct. You can use this, and also you can use this, but in this you should know the concept of kinetic and potential energies. So next problem is 58. A proton moves in z plus direction after being accelerated from rest through a potential difference of v. A proton then passes through a region with a uniform electric field E and the plus x direction, and uniform magnetic field B and plus y direction, but a proton trajectory not affected. If the experiments were repeated using a potential difference of 2 volt, the proton would then deflect in plus x direction, minus x, plus y, minus y, or remain undeflected. We have a proton that is moving in z plus direction. So our velocity is velocity in z direction. So this is, we take velocity as n k direction, unit vector with velocity as k. And also we know that a potential difference of v is applied. A proton moves in plus z direction after being accelerated from rest through a potential difference of v. The proton then passes through a region with a uniform electric field E and plus x direction. So our electric field, this is ni unit vector in plus x direction, and a uniform magnetic field B is applied in y direction. This is, we can write B, this is equal to nj unit vector. Now in the first case we have that the proton, this is moving accelerated due to potential difference of v, and this is moving and enter to a region where there is magnetic field B, but still the proton remain undeflected. So we have an electromagnetic field in electromagnetic field region. So in electromagnetic field region, force always equal to E into V, E into E is a charge, E plus E cross V cross B. This is a force on a charge particle of charge E when it is moving in E plus V cross B field. So we use E into, this is n I direction, plus V, this is n k direction, multiplied by B, this is n j direction. So V cross B, this will give us a product. This is equal to this is a charge EI. So we can write plus V cross B, and to K cross J will give us minus I J K. This is a reverse order, J, K and J. So K cross J will give us a third unit vector I, but in negative direction. So the force, this will be equal to charge into electric field minus the product of speed and the product of velocity and magnetic field, but in I direction. Now the problem is stating that in the first case, when this proton entering into the B field, the path or the trajectory of the proton remain unchanged. This means that this force F1, we say this is equal to 0. We say that the force on the proton is 0 in this electromagnetic field, therefore it remain undeflected. So this means that this term equal to 0. So this means that E minus V cross B, this is equal to 0. This implies that V is equal to E cross B. So because this ratio is same, so velocity remain the same. The velocity is given by the ratio of electric to magnetic field, and because it remain the same, therefore this equal to 0, this term equal to 0. This is our equation number 1. Now the second case, in the second case we have given that a potential difference, accelerating potential, is increased to its double. So the kinetic energy, this is equal to 1 by 2 mv square, this is equal to ve. So if you find velocity, so this is equal to v, this is equal to 2 and to potential difference divided multiplied by charge divided by m and to square root. This is our v1. For v2, this is equal to 2 and to 2ve divided by m square root, because potential difference get double. So if become double, so we can write that v2, this is equal to square root 2 of v1. We can write that square root 2 and to 2ve divided by m square root. So this is equal to v1 and this is equal to square root 2. So v2, this is equal to square root 2 and to v1. So v2 is equal to v square root 2 v. So we can see that if we put this here, this in this equation, so this equation become F is equal to E into EI minus v1, this was v1, so this is v2, so v2 is a square root 2 into v1 and to b. So this is our 4. Now this was 0 when a charge was undeflected. Now this term get increased by square root 2. So if this term get increased by square root 2, means the difference of these two term, E electric field and I direction minus this is the product of square root 2 and 2v bi in I direction, is less than 0, because this term get increased by square root 2. So this is a negative, so the difference of these two will be less than 0. Means this, if this is F2, the second force when we get the potential difference doubled, so this is a force applied on the proton when it become double, when force become double, when potential difference is doubled. So this force will always less than 0. Less than 0 means the net force was 0 when the potential difference was v, and the net force get decreased, the net force get decreased, means in reversed in the direction when a potential difference is doubled, means the particle was to move in, means the particle will move, this is I, this is for x direction. So so if the force is greater than 0, the particle will move in x direction but in plus, and if the force is less than 0, this means that the particle will move in x direction but in negative x. So the force is less than 0, this means it moving in minus direction, and this is a unit vector I with this term. This means this is an x direction, so in negative x direction the proton will move. In another concept we can also use that a particle is moving in plus z direction, electric field in plus x direction, magnetic field in plus z direction. The particle should move in plus x direction when a potential difference is increased, but this is for negative particle. If it was electron, then the particle should move in plus x direction, but we have a proton which is positive charge, so this should move in opposite direction. This is the negative of x plus x, this is minus x direction. Next problem 59. For an inductor and capacitor connected in series, the equation describe the motion of a charge is L into d square by dt square q plus 1 over c q equal to 0. This is an equation for a series circuit of inductor and capacitor connected in series, where L is inductor inductance, C is capacitance, Q is charge stored in this capacitor. An analog equation can be written for a simple harmonic oscillator with a position x, mass m and spring constant k. Which of the following correctly list? So we have to compare two equations. The first oscillation equation for a circuit having inductor and capacitor, and the second oscillation equation, simple harmonic oscillator equation for mass spring system, where x is the displacement, m is mass and k is a spring constant. For harmonic oscillator we have an equation, this is equal to mx plus mx double dot plus kx, this equal to 0. We can write this equation as m into d square by dt square by dt square x plus k into x equal to 0. If we compare this equation with this is equal to d square by dt square q plus 1 by c q, this equal to 0. Comparing this equation, x q will replace x in this equation, and 1 over c, this will replace k in this equation, L will replace m in this equation, and similarly here is x and q, and this is d square by dt square, d square by dt square, means q, this is equal to q, this should equal to x, and c, this equal to 1 by k, and L, this should equal to m. So we can see that in part A, L equal to m, q equal to x, and c equal to 1 over k. So part B is our right option. This lists the right relation between these two equations, a right analog, mechanical analog for this electronic circuit. Next problem 60. An infinite uniformly charged sheet with a surface charge density sigma cuts through a spherical Gaussian surface of radius r at a distance x from center as shown in figure. The flux phi through the Gaussian surface is. We have an infinite sheet. We have first of all let's say this is a Gaussian surface and this is the radius r of this Gaussian surface. This is a Gaussian surface and this is a radius r, and this surface enclosed charge, total charge enclosed q enclosed, and the charge distribution, surface charge distribution is sigma. So the flux this always gives according to the law that q enclosed, charge enclosed divided by epsilon naught. This is the flux through any Gaussian surface according to the Gauss's law. Now the charge enclosed, this always equal, in this case according to the surface charge density, this is equal to surface charge density equal to q enclosed divided by area, implies that charge enclosed, this is equal to sigma A. So the flux through the Gaussian surface when its radius is r and charge enclosed q, or its surface charge distribution is sigma, this is equal to sigma A divided by epsilon naught. This we can write sigma pi r square over epsilon naught. This is our flux when it is a circle within, when it is a Gaussian surface having a radius r. Now the problem is that an infinite uniformly charged sheet having charge density sigma cut this Gaussian surface at a distance x from its center, means in this case the Gaussian surface will reduce to this one having radius x. In this case the flux, this is equal to phi 1, the flux second will be equal to sigma pi x will replace with x square divided by epsilon naught. So this is a flux for this circle and this is a flux for total circle. This is phi 1 phi 2. So the flux through the infinite sheet will become the difference of these two. So the net flux through the infinite sheet having surface charge density sigma, this will be equal to phi 1 minus phi 2. Phi 1 is sigma pi r square divided by epsilon naught minus sigma pi x square divided by epsilon naught. Taking common, we can see that pi into r square minus x square into sigma divided by epsilon naught. So this is our net flux. This is equal to pi into r square minus x square. So this is our net flux. This is equal to phi net. This is phi net. This is equal to pi r square minus x square into sigma surface charge distribution divided by epsilon naught. So this is our right option. We can see this right option in option C, pi r, sorry, in option D, pi r square minus x square sigma divided by epsilon naught. So this is our right option. Keep in touch for further videos and further solution of GRE to prepare your test for jobs inductions, and please subscribe, like and share our channel. Thanks.